In this example, we're going to work with the piecewise function f of x equals 2x minus 3 when x is less than 2, f of x equals negative 2 when x is equal to 2, and f of x equals x squared plus 3 when x is greater than 2. For this function, we're going to find some limits using analytic methods. Specifically, the analytic method we're going to look to employ will be direct substitution. As we examine the individual limit questions, we'll have to determine when it's appropriate to use direct substitution and how to use it for each question. To start, we're going to look at the limit as x approaches 2 from the left for f of x. Now, by definition, if we're approaching 2 from the left, we're approaching 2 from values of x that are less than 2. So looking at our function, if we're looking at values of x that are less than 2, that means we're looking at y equals 2x minus 3. That's how y is defined for values of x that are less than 2. So here it will be appropriate for us to evaluate the limit as x approaches 2 from the left for f of x by evaluating the limit as x approaches 2 from the left of 2x minus 3. So here we can use direct substitution, and when we replace x with 2, we find that the limit as x approaches 2 from the left for our function f of x is equal to 1. Now we'll look at the limit as x approaches 2 from the right for our function f of x. Again, by definition, as x is approaching 2 from the right, x is approaching 2 from values of x that are greater than 2. And when x is greater than 2, y is defined as x squared plus 3. So as we approach 2 from the right, we're approaching along the x squared plus 3 path of the graph. This then enables us to interpret the limit as x approaches 2 from the right of f of x to be equal to the limit as x approaches 2 from the right of x squared plus 3. And here again, direct substitution may be used and will give us the limit as x approaches 2 from the right of f of x being equal to 7. Now we're going to look at the overall limit as x approaches 2 of f of x. Our determination of that limit is dictated by the following theorem. This theorem describes the relationship between one-sided and two-sided limits and says, assuming f is defined for all x near a except possibly at a, then the limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the right of f of x is equal to L, and the limit as x approaches a from the left of f of x is equal to L. Translating that, the theorem states that an overall limit as x approaches a particular value for a function will exist if and only if both the left and the right-hand limits at that value exist, and both of those limits must be equal to each other. So clearly here, the left-hand limit as x is approaching 2 is 1. The right-hand limit as x is approaching 2 is 7. So since the left and the right-hand limits are different, according to the theorem, the overall limit for this function as x approaches 2 does not exist. Now, if we were to talk about direct substitution to find the limit as x approaches 2, then we'd be looking at evaluating that limit using the definition for y when x is equal to 2. And we see that when x is equal to 2, y would be equal to negative 2. Clearly, by our theorem, the overall limit as x approaches 2 isn't negative 2. In fact, it doesn't exist. So direct substitution is not applicable here. Specifically, the limit as x approaches 2 of f of x does not equal f of 2. So no direct substitution to answer the overall limit question. Now let's revisit our piecewise function. Let's look at our findings. we saw that the limit as x approached 2 from the left of f of x is 1, and the limit as x approached 2 from the right is 7. Here's a picture of the graph of this function. And looking at the graph of this function, we see that our analytic results are going to be verified. The limit as x approaches 2 from the left. Approaching 2 from the left, we'd be following this path. And as x is approaching 2, y is approaching 1. So the left-hand limit as x is approaching 2 is 1. Now looking at the right-hand limit, as x approaches 2 from the right, we'd be following this path. And as x is approaching 2 from the right, y is approaching 7. So the right-hand limit as x is approaching 2 is 7. And the overall limit doesn't exist. Again, we can visually see it on the graph. We saw through our analytic analysis and the use of the theorem the non-existence of the overall limit.